Hello. So I was going to make a video explaining the difference between special relativity and general relativity, but then I realized that the best way to distinguish between the two concepts is to clearly define both. So that's what I'm going to do first, and I'll make follow-up videos later on with more examples and a clear side-by-side comparison between general relativity and special relativity. But today's video is going to be dedicated towards defining special relativity.
I feel like an astronaut in what you know about rolling down in the deep.
What is special relativity? Well, what makes something relative? Understanding that what you observe is relative simply means you are aware that your perspective may differ from the way someone or something else perceives their surroundings. The way you view the world, for instance, will be different from how a bird flying through the sky views the world. Relativity is the realization that your perspective is based upon your environment. Well, actually, you don't really need to realize it. Relativity is having a perspective based upon your environment. Now, special relativity is a physical theory, and so it is a little more grounded in mathematics than just the concept of relativity itself. The theory comes from a paper Einstein published in 1905 entitled On the Electrodynamics of Moving Bodies. Obviously, Einstein did not invent any physics. I say comes from because the way we describe and discuss special relativity largely comes from Einstein's publication. Special relativity is grounded in two principles. 1, the laws of physics hold true for an observer in an inertial reference frame, and 2, light moves at the same speed in a vacuum regardless of which reference frame you are in. Okay, let's break that down a bit. The laws of physics hold true for an observer in an inertial reference frame. An inertial reference frame is a frame that moves at a constant speed. If we consider a runner on a track field before they begin their race, the runner will be unmoving. Because they are unmoving, or we could say alternatively that they are moving at a constant speed of 0 miles per hour, or 0 kilometers per second, or 0 whatever units you want to use, regardless it's 0. The runner is in an inertial reference frame at this time. Now, as the runner begins their race, they will accelerate up to a certain speed. At this point, they are not in an inertial reference frame because their speed is increasing. Once the runner reaches a steady pace, they will once again be in an inertial reference frame. Now, as the runner is moving at a constant pace, let's say 12 miles per hour, a bird is also flying through the sky at 30 miles per hour relative to a stationary reference frame. A stationary person is in the audience and views the runner moving at 12 miles per hour. The runner themselves knows that they are moving because they feel joint pain and probably remember putting in the effort to get to a certain speed, but if the runner didn't have to deal with joint pain and whatnot, then they would not notice themselves moving. Why? Because their reference frame is defined precisely by their speed, and they are thus moving at the exact same pace as their reference frame. The bird, on the other hand, will view the runner as moving backwards at a speed of 18 miles per hour. If all the observers instead look at the bird, the stationary observer will see the bird moving at 30 miles per hour, the runner will see the bird moving at 18 miles per hour, and the bird will see itself moving at, 0 miles per hour. The other principle of relativity states that light moves at the same speed regardless of which reference frame you are in. This means that if a beam of light goes past our track scene, the bird, the runner, and the stationary observer will all see the beam of light moving at approximately 300 million meters per second. This is counterintuitive because the first principle of special relativity would seem to imply that the stationary observer views the light as moving faster than what the bird observes. But alas, the reason we say that the speed of light is constant in a vacuum is because this is what's measured by experimentation, but there's not really currently a good explanation as to why this phenomenon occurs. So how do we find peace of mind when the principles of special relativity don't operate quite as we'd expect them to? Well, you either accept it, research it, or wait for someone else to research it for you. Einstein himself continued to contemplate the complexities of relativity after his 1905 publication. That led to general relativity, which, relatively speaking, is even more trippy than special relativity. But on to that later.
In slow motion, yeah. I feel like an astronaut in the ocean, like what you know